possible, or else you want me to start the session, ma'am? Okay, ma'am. Okay, thank you. Thanks for the opportunity. So now I'm sharing my screen, ma'am. I hope it is visible, ma'am. Okay. So good afternoon, everyone. So today the topic will be challenges in quantum hardware, qubit stability, and scalability. So there are a lot. What first of all, just what is quantum computing in machine learning? So quantum computing is something which is used in quantum computers. So, for example, we have normal computers and quantum computers. What is the difference between uh, I mean, normal computers and quantum computers is that like if there is a problem that we solve in some minutes in normal computer, but coming to the quantum computer, we can solve that problem in milliseconds. So that is the major difference between quantum computers and normal computers. So here is the slide. So you can see here what is quantum hardware. Our topic is that challenges in quantum hardware. Quantum hardware is nothing but the structure of the quantum computer. I mean, the inner side parts and outer, what you can see. So that we call as hardware. So, what is quantum hardware? Quantum hardware refers to the physical devices. We just, brushed up that what is hardware, physical devices and systems used to build and operate a quantum computer. Okay, so unlike classical computers that use bits, 0 or 1, quantum hardware uses qubits. We can exist in superposition like 0 or 1 at the same time. But in physical computer, we can use 0 or 1, whether it is 0. If we are placing 0, we can't place 1. But in the quantum computers, we can use both the qubits, like 0 and 1, at the same time and can be entangled with each other. So, for example, if you are taking a ribbon, two ribbons at once, you can see if we are folding the both the ribbons at once, we can see the entanglement. Same happens here also. So different technologies are being developed as quantum hardware platforms such as superconducting qubits in IBM, Google, and Rigetti, trapped ions, IonQ or Honeywell, photonic qubits. So you can see the examples over here. Spin qubits in semiconductors, just like Intel, Silicon, quantum computing. So that is about quantum hardware. And coming to the qubit stability. Qubit stability, simply we can say that, uh, for example, qubit like 0 or 1 to maintain its state, quantum state. So that is called qubit stability. So here you can see qubit stability generally refers to the ability of a qubit to maintain its quantum state. like superposition or entanglement, without any errors. So, the major drawback in this quantum computers is that we are getting lot many errors in milliseconds. We can brush out in the coming slides. So, this is often described using coherence time, T1 and T2. So, T1 is nothing but relaxation time. It's like how long a qubit stays in its excited state before decaying. T2 comes under decoherence time. How long a qubit maintains its superposition before noise, I mean 0 or 1 before noise, or interference causes it to collapse. So that is nothing but qubit stability. And coming to scalability in quantum computing. Scalability refers to the ability to increase the number of qubits in quantum computers. It means that in normal computer we can't do this, but coming to the quantum computers we can increase the qubits as much we want, but we can't do in the normal computer. Still we are trying to uh, make that stable, even though we are increasing the qubits to it. Stable, controllable, and interconnected. Challenges in scalability include control thousands or millions of qubits simultaneously. We refer to this quantum hardware in that we have seen that we can increase number of qubits how much we are trying to put in. So because of that, the scalability variation will occur in this, reducing error rates as the system grows. If we are increasing the qubits, the error rate will be increased. So, to reduce that, scalability should be mandatory in this. So, building error correction methods. Since real qubits are very noisy, we can here you can see that from the hardware part, because of increasing the qubits we gonna get a lot of noise from it. Managing cooling system. Here if we are using the wires in the hardware, it means that the heat part will be increased. To reduce that, we should use the coolants here. So managing cooling systems. Superconductors conducting qubits often need to be absolute zero. Sometimes it should be minus to control the temperature of it. So, moving to the next slide, you can see here the picture of the quantum promise and the hardware reality. Managing the hardware is very difficult in quantum computers. We can see further. This is the frontier part of quantum hardware. Why it matters? Quantum computers promise to solve problems unreachable by classical machines. As we discussed in the previous slides, that normal computers can't do all the stuff which we are looking for. This generation is completely into AI and machine learning. So we have to upgrade ourselves to quantum computers. But here we are facing lot many issues. Here, quantum computers are used from the drug discovery to cryptography. I hope you guys already know about lot many medicines which are introduced using quantum computers only. Cryptography, as you all as we all know that Bitcoin, lot many Ethereum, this all comes under cryptography. So quantum computers are used in from drug discovery to cryptography. I mean, quantum computers does everything, but they we are reading about the drawbacks of. But building reliable large scale quantum hardware remains the big hurdle to unlocking this potential. So everything is having pros and cons. So if we are, overcoming this cons means we can see a big life with very smooth um, very smooth technology. I mean, we can use all the technologies in very smooth way if we are unlocking this potential without any hurdles. So today's exploration, the twin challenge of qubit stability and scaling quantum systems. So this twin challenge is the biggest challenge in quantum computers. Moving to the next slide. So the error avalanche, why stability is hard to maintain. Here we can see some of the things why the stability is hard to maintain. The first one is that gate error rates. Quantum gates have inherent error rates of approximately 1%. Here you can see 1%. 1 is very small number. But coming to the quantum computer errors, in 1% we can lose lot many data. For example, for two qubit operations seemingly small but catastrophic at scale. So catastrophic in the sense, if we are taking a problem like in the normal computer, if we are solving that problem in some minutes, but in the quantum computer if we are solving in microseconds, but in that microseconds error rises means we are going to lose so much of data. It's cost in $1 billion. So we have to overcome this errors. Second one is error multiplication. As we have discussed now, in a 1,000 qubit system, errors multiply exponentially. For example, 10,000 in exponential, the value is huge. So we are getting lot many loss in this errors. So threatening the reliability of any meaningful computation. The third one is that error correction overhead. Quantum error correction requires thousands of physical qubits per logical qubit, currently impractical for real world applications. Lot many companies like IBM, Google, even our company are working in this with millions of dollars putting in. Why? Because if we are overcoming this error means we can see a great world. Moving to the next slide. Qubit instability, the fragile heart of quantum computing. Here is the actual drawback comes into place. The first one is that decoherence. Qubits rapidly lose their quantum state, coherence, due to environmental noise and interactions. As we have seen, because of that hardware, we are getting lot many noise from the quantum computer often within microseconds to milliseconds. This loss of information is a critical barrier. In the last slide, we discussed about this. I mean, the data which we are losing in milliseconds can, it's a big loss. So it's a critical barrier. So second one is the limited coherence times. For instance, IBM's cutting edge superconducting qubits typically maintaining coherence for only around 100 to 200 microseconds, severely limiting computation duration and complexity. Coming to the other one, high gate error rates. Even the small errors, 0 point micro percentage to 1%. So during qubit operations, multiply in large systems, quickly correcting results and undermining the overall reliability of quantum computations. The same thing. If we can see in micro percentage, but the loss of this error gates will be huge. Decoherence, the silent killer of quantum states. So, environmental noise destroys delicate quantum superposition in microseconds. as we discussed before, making qubit stability the ultimate engineering challenge. This is the challenge to lot many scientists to overcome these errors. Milliseconds to madness. The same thing repeats here is that we can lose the data in milliseconds. So it generates chaos in this. The race against decoherence, fleeting coherence. I hope you're getting all this information right. Is there any doubts? Ma'am, any doubts till now? Okay, ma'am. Sure, ma'am. Sure. Yeah. So the first thing is fleeting coherence. Qubits maintain their delicate quantum state for only milliseconds, if not microseconds, before succumbing to decoherence. Qubits maintain their delicate quantum state for, I mean, the qubits which we are putting in, they only maintain the delicate quantum state only for milliseconds, not more than that. So, because of this, decoherence is happening, environmental chaos. Even the slightest interaction with the environment, it will be scary because the noise which gonna appear around the hardware, it generates the chaos. Be it stray photons or vibrations, can collapse a qubit's quantum state. Because of this noise, it's gonna collapse the entire qubit's quantum state. Third one will be data corruption. We discussed in each and every slide, we are losing the data because of that error. So we're gonna lose a huge number of data. This rapid loss of coherence leads to critical errors, making computations unreliable and quantum advantage elusive. Elusive in the sense difficult to make precise. So, because of this data corruption, we can't do the calculations precisely, I mean, very correctly. So, these are the um, madness which we are getting if the quantum computers are getting errors. Coming to the next slide, scaling challenges from tens to thousands of qubits. We can put in the qubits in, I mean, from 1 to thousands. You can add as much as you can. But the thing is, in the increasing of the qubits is always proportional to the errors. How much qubits we are putting in, that leads to the errors. So we have to scale this. You can see in the picture, this scaling challenges in tradition tends to the thousands of qubits. The first one is that amplified noise and crosstalk. As qubit count increases, so does the interference between them, making it harder to isolate and control individual qubits accurately. So, as we are increasing the qubits, it's gonna isolate to each other, and we can lose the control um, to calculate accurately in the addition of the qubits. Coming to the other complex control, we can't manage to control all the qubits at once. Controlling and reading out thousands of qubits requires exponentially more precise and numerous signals overwhelming current control systems. The next one is wiring bottlenecks. In the hardware, we can see number of wires will be there. Thousands of physical control lines necessary for operation. So we need lot many wire setting for this hardware. Generate heat and occupy space, becoming impractical for large scale cryogenic quantum systems. Cryogenic quantum systems is nothing but the cooling part which we are providing to the quantum systems, nothing but quantum computers. So, wiring bottlenecks in the sense in the very limited space, we are putting lot many wires into it. Because of that wiring, the heat may produce hues. To overcome that heat, we are putting cryogenic quantum systems. It is nothing but the cooling part. The cooling part is not from zero, it's minus degrees to the minimum. Next comes to exponential calibration. Each additional qubit dramatically increases the complexity of fine tuning and calibrating the entire system for optimal performance. The strategy for every system is that we have to put the optimal performance in the sense we should get maximum efficiency from that. This is our motto. Moving to the next slide. Error rate explosion. A 1% error per 2 qubit gate becomes catastrophic. I mean, very harmful for that. Because 1% error, we can see 1% error in that gonna happen in milliseconds or microseconds. But the damage is very huge. We can't even imagine. So, 1000 qubits could see computation failure within nanoseconds. So, as we have seen in the previous slides, that 1000 qubits, for example, 1000 qubits we are putting into the computation, but the damage which gonna arise in the nanoseconds time only. So, we have to overcome this error rate. Next one is that hardware inflation. What is this hardware inflation? Quantum error correction demands thousands of physical qubits per logical qubit. In the normal computer, we can see it's some gates, but here, logical gates in the normal computer is different. Here, the quantum computer is different, inflating hardware requirements exponentially. The other thing is that control bottlenecks. Thousands of microwave or laser control lines strain cryogenic and optimal system beyond current engineering limits. The same thing, cryogenic in the sense we are giving the cooling system to the computer so that we can overcome the heat. We can overcome the laser control lines. You can see here in this image. This is nothing but the twin things in the quantum computer. This is the quantum control. Till now, we have seen all the drawbacks in the quantum computer. From now, we can see the what is the control for this all drawbacks. So, quantum control. The first thing is that critical interface layer. First one is that signal translation. Control hardware translates classical signals into precise qubit manipulations with nanosecond time. Our motto is to introduce quantum computers without any drawbacks. We have to calculate any kind of solution, I mean, any kind of question in nanoseconds without any damage. We have to get the precise answer to that question. That is the ultimate motto of the nano computer. So here is that one particular thing. And second particular thing is that real time adaptation. For example, if we are getting any calculation on time, If we see in some electronic motors per minute, I mean, for example, now the time is 2:37. The value of that particular machine is something, but if we see at 3 o'clock, the value will be changed, should be changed. So a real time adaptation should be there. I mean, we have to calculate per time, should be very precise. We can get that solution using this quantum computers without these errors. Third one is that scaling complexity requires synchronization. For example, if we are taking some motor, synchronization is very important in that. The same thing repeats here in the quantum computer. Requires synchronization, efficiency, and programming flexibility across thousands of control channels. This is all we need without any errors. Moving to the next slide. Diverse qubit technologies trade off in stability and scale. So, this is nothing but we have to do this all the things without any so much of loss. Here we can see both pros and cons from the starting of this session. So here, superconducting qubits. The pros are there and cons are there for everything, for every system, which we use in the daily life things. Like at home, we can see the fan, this computer, laptop, and other things also. For every machine, there will be pros and cons. Here also, there are pros and there are cons. What are the pros? Fast gate operations, relatively mature fabrication. And coming to the cons, require extreme ultra cold temperatures. We have seen that in the hardware, because of that bottleneck wiring, um, the heat may produced is huge. Because of that heat, we need refrigerators. We have seen that in very cold temperatures, it goes to minus degrees only. To maintain that temperature, we need this. So that would be pros and that would be cons here. Superconducting qubits. Coming to trapped ion qubits. The pros would be long coherence times, high fidelity gates. So here the pros will be long coherence times. Uh, if we are using it, last time we have seen that coherence timing is in milliseconds. But using this, we can increase the coherence times. That would be the pros. And coming to cons, complex laser control, challenging to scale beyond dozens of ions. This would be the cons here. So the laser control is very complex here. Coming to the third one, neutral atom qubits. The pros will be highly scalable arrays, flexible atom arrangements. If we are using this neutral atom qubits, the scalable arrays will be very high, and atom arrangement is also flexible. But before that, without this, the atom arrangement is very complex. So this would be the pros here. But coming to the cons, difficult atom trapping, vacuum stability issues, slower gate speed. These are all the cons. There will be a difficult thing is that atom trapping. We can't trap atom very easily. It would be very complex. Coming to the next one, it's topological qubits. You can see the structure of the topology. The qubits sometimes the arrangement would be in that case. In that case, the pros will be promise inherent error resistance by encoding information topologically. The same thing. Uh, the shape of the topology qubits is something that the coherence is very good in that shape. But coming to the cons, still highly experimental. Again, the complexity rises here. Theoretically, concepts in early stages. These are the cons. So, what is the breakthrough to all these things? Is that modular quantum system on chip architecture. It's nothing but QSOC architecture. The first one is that integrated qubit architecture. So, MIT researchers are pioneering a module called modular quantum system on chip. So, MIT researchers, what they are doing is to overcome all these drawbacks. They are, working on modular quantum system on chip. So, architecture integrating thousands of diamond color centered qubits directly onto the CMOs. Here you can see in this picture, these researchers, what they are doing is they are working on this chip, which is in diamond color. So, what they are doing is integrating thousands of these qubits directly onto the complementary metal oxide semiconductor, which is nothing but CMOS chips. So, this innovation is there is a chance in this innovation to approach to overcome these traditions. The second one is that quantum radio control. What this system does is it utilizes quantum radios to tune diverse, inherently inhomogeneous qubits into resonance. This enables scalable and precise control over the individual qubits. By setting up this quantum radio in the system, it tunes the diverse, inherently inhomogeneous qubits. I mean, the very ununiform. It's not in the uniform. So, in that, into resonance. This enables the scalable and gonna give the precise control over the individual qubits. They can't be scattered in different directions because of using of this, we can put in the uniform way. Coming to the other thing is that optical networking potential. This architecture opens pathways for potential optical networking between chips, paving the way for truly large scale quantum systems and enhanced computational power. So, the thing is, for very small scale quantum systems, we can we can drive the solutions very easily, but coming to the large scale quantum systems, it will take very very complexity. So here what it does means this architecture opens pathway for potential optical networking between chips and paving the way for the very large scale quantum systems. Going to the next slide. Software and algorithmic challenges in scale. Noise adaptation. As we have seen in the hardware, there is a, I mean, definitely it's gonna happen, the noise gonna happen. What we have to overcome that is that noise adaptation. Real quantum systems have noise and connectivity constraints that algorithms must navigate intelligently. So this noise adaptation, what it does means real quantum systems have noise and connectivity constraints. We have seen that algorithms must navigate intelligently. What we have to do is so to overcome that, these algorithms are very useful to overcome this noise things. Coming to the other thing, circuit optimization. Quantum compilers must optimize qubit layout to reduce error prone operations and respect hardware topology. So, what we have to do in this is that optimizing the complete circuit in the quantum computers. The compilers to optimize the qubit layout. So, in this, we have to optimize the circuit in that way that to reduce the errors to it. If we are reducing the errors, the efficiency of the system is high. So we have to use this circuit optimization. The other thing is that verification complexity. So in this quantum system, the complexity is to use. So to analyze this complexity and make the complexity in a very easy manner. For that, what we have to do is classical verification and debugging become exponentially harder as qubit counts grow beyond classical simulation. So, the same thing, classical verification. So, what we have to do is to overcome this complexity, we have to um, follow the classical patterns to verify all this stuff, and debugging become exponential. So why we are getting errors means the exponential, if we are putting the qubit values, it takes in the exponential, so it is very harder to maintain that in the exponential way. So before that, we should verify all the complexity. So we have to follow the classical simulation for it. So coming to this next slide, the software and algorithmic bottleneck. So in the previous slides, we have seen the hardware of the bottleneck wiring. So bottleneck wiring in very short very short space, we are doing the wiring part. What it happens means in very short span, in very short way, the wires will, tangle to each other, and they're gonna produce the heat from it. So to overcome this, the algorithm should be changed. First thing is that noise aware compilers. Compilers must optimize quantum circuits to minimize the impact of hardware noise and errors, crucial for reliable results on noisy intermediate scale quantum devices. So, because of that, the noise of the hardware is used. To overcome that noise, we have to use the compilers to optimize quantum circuits to minimum the impact of the noise and the errors. If we are decreasing the noise means we can increase the efficiency. So this should denoise the total system. So noisy intermediate scale quantum devices. These devices are used to denoise the system, quantum system. Coming to the other thing is that error mitigation techniques. Using these techniques, we can overcome the errors. Advanced algorithms are needed to detect and correct errors without fully fault tolerance. The things what happens is that because of that errors, the complete system may collapse in some cases. But this error mitigation techniques in this techniques, advanced algorithms, using advanced algorithms, we can overcome these errors without any fault tolerance, effectively extending the lifetime of quantum computation. Using these techniques, we can increase the lifetime of quantum computers also. So it is very important technique we should use in the uh, quantum computers without any, I mean, I won't say without any errors, but still after using also we may get errors, but those are negligible. Coming to the algorithm to hardware mapping. So in this, what happens is like efficiently mapping abstract quantum algorithms to the physical constraints and limited connectivity of real qubits presents an exponentially complex problem. Using this algorithm to hardware mapping, I mean, the algorithms which we create that should match with the hardware mapping in the system. That should happen. If the hardware mapping is uh, is not coping up with the algorithms, means the complete system may collapse. So what we have to do is we have to match the algorithm to the hardware mapping in the system. To run the system efficiently means we are using the algorithms to the physical constraints and limited connectivity of real qubit presence. Moving to the next slide. I know it's a bit boring, but this will help you. The road ahead, interdisciplinary innovation and investment. After doing lot many things to overcome the drawbacks, we are, you know, taking some solution to it. The first thing is that hardware stability. First thing is that we are setting in the system. Both plays very important role is that one is hardware and one is algorithm, which we have seen in the last slide. So the stability, if the system is very stable, the efficiency will be the use. So we have to put the hardware in a very stable manner. Continuous advancements are required in qubit design and material science to extend coherence times and reduce error rates. Because of this hardware stability, we can overcome this qubit design. You can see qubit design in topological way. It, it means if we are putting more thousands of qubits into it, it may give the complexity to overcome all these qubit designs. This hardware stability gives plays a very important role uh, in this to overcome the error rates. Second one is that cryptogenics and control. Cryptogenic is nothing but the coolant part in the system. We have seen in the previous slide cryptogenic. It means that the system which we are giving to the hardware, the cooling system to the hardware. In this, the innovation is cooling technologies and compact control electronics in essential for scaling quantum systems efficiently. Same thing. I mean, we have to give the cooling technologies to the hardware part so that the scaling quantum systems work efficiently. The scaling should be very good way, should be in the good way so that quantum system gonna work very efficient. Third one is that software tooling, development of robust quantum compilers, robust in the sense very strong. If we are developing very strong compilers means it will help the system to give the efficiency. Error mitigation libraries and programming framework will unlock the potential. The high potential we are gonna get from the system if we are using this software tool. The design of the software tooling should be very strong. The compilers should be very strong so that we can get the maximum potential from the system. Coming to the next thing, it's industry and academy. So same thing. If we are developing this quantum computers in very potential way, means that's gonna help for the future in the industry and in academia also. In lot many institutions, these quantum computers uh, gives a boon to everything. I mean, I know it may gonna lose the jobs, but still it's gonna do 100 people work 100 people work by this computer. So major players like IBM, Google, and Microsoft and some other companies also, our company also, alongside startups and academic institutions, are investing billions to achieve 1,000 plus qubit systems. Same thing. All these companies are investing in billion dollars in this quantum computers. They are working like anything to get the more efficiency from the quantum computers, because normal computers can't do all the work, but the quantum computers gonna boom the uh, technology. I mean, in that we are using machine learning, artificial intelligence. So 100 people work can be done by one quantum computer. But the thing is that without all these errors, we are going to get the maximum efficiency. But the which the things are getting, worst is that the errors. We have to design the quantum computers without any errors. That is not happening. But the researchers are not stopping here, because they are getting all the solution to overcome this drawbacks. Coming to the fifth one, key milestones. Focus on hybrid quantum classical architectures and the eventual realization of error corrected logical qubits with defined progress. The ultimate thing is that we have to get the more efficiency, maximum efficiency from the quantum computers. That is the ultimate motto of ourselves. So, this is the road ahead. And coming to the next slide, collaborative innovation. Any doubts till now? Collaborative innovation. So, researchers are, in getting inventions to this quantum computers to work in a right way. Scaling quantum hardware demands breakthrough in physics, engineering, and computer science, working in unprecedented, never got before having. It means that before 90s, before 2000, this was not happened. This artificial intelligence was not there. The quantum computers are not there. These were happening nowadays, but there is no word such as quantum computer in the 90s days. So we are getting, very technological way. We are changing our lifestyle in completely technology. Robots are there. Robots can do whatever the humans are doing. Robots also doing. The robots are, I mean, the algorithms which we are putting in that is that machine learning and artificial intelligence. The emotions which we are feeling, we can see in the humans. The same thing, that same algorithms we are putting in the robots also using artificial intelligence and machine learning. So the technology is booming nowadays. It's bringing harmony to the people. We may you know do our work in very smooth way. So hybrid quantum classical architectures and improved quantum control hardware offer practical paths forward through incremental innovation. Same thing. I mean, the toughest job which we can't do can be done by the quantum computers. So the people which we are, engineers and and computer science, which the researchers are working in this, are still working to get the more precise quantum computers so that every task can be done in milliseconds, which the human can't do. So because of this, lot many jobs will be in trouble. Industry leaders like IBM, Google, Microsoft, IonQ, and some other companies also are racing. I mean, are they are you know comparing and giving the competition to each other to build fault tolerant, scalable quantum systems that can deliver real world impact. So, all these companies, which the top MNCs, are putting millions of dollars, millions of people in the research to give quantum computers without any errors, like fault tolerant scalable quantum systems can be delivered to the real time impact. I mean, any human being can use that facility without errors, only the quantum computers can give the efficiency. So, top companies are working on this and they're spending lot many $1 million. Trust me, I'm from the corporate background. I know the business, how much money they are putting in this. So it's putting our lives in a proper way. I mean, without any chaos, these quantum computers can bring our lives very easy. Coming to the next slide. I mean, the conclusion. Overcoming fragility to unlock quantum potential. See, the hardware which we are using, the quantum computers, the fragile, the I mean, the semiconductors in that complete system, it is very delicate, very soft in nature. So that qubit stability and scalability should be bring without putting any chaos. So with that fragility, we can't put all these good things very easily. So we should overcome that. Qubit stability and scalability stand as the most profound challenges in quantum hardware development. The journey to a fully fictional quantum computer is arduous. I mean, much energy needed. So, to overcome all these things, the researcher are putting so much of energy, money, time to overcome all this chaos, demanding a unified front of interdisciplinary innovation. Success hinges on collaborative efforts across physics. Same, physics is everywhere in this quantum computers, engineering, and computer science. The quantum revolution is not just about theoretical breakthroughs, but about turning today's fragile, very delicate experimental qubits into tomorrow's reliable transformative processors. I mean, using these computers, you can't even imagine our lifestyles in the future. But it leads to job loss also. But if we are getting these systems, in our future means that systems gonna ease our lifestyle. So in this thing, physics, engineering, and computer science plays a major role to ease our lifestyles. Because if you can see the quantum computer structure, semiconductors will be used. I mean, engineering part is happening here. Machine learning is using in this quantum computers. Computer science is, plays major role in this, and physics to put the hardware and the algorithms in the proper way. Physics is playing very major role in this. So these are the major roles playing in the quantum computers. The quantum revolution is not just about theoretical breakthroughs. I mean, we can the quantum computers are not only used to solve the theories and all. Practically, also, it gives an immense change in our daily lifestyle. So today we are facing lot many hurdles, but tomorrow the quantum computers, can launch without any errors. If they are launching the quantum computers without any errors, the lifestyles of art will be very fascinating, very easy way. You can see a clinic in everybody's how. I mean, if you see the lifestyle of US people are completely in the next level. I mean, that country is very developed, already developed. But we can't see in India because India is developing. I mean, we are still, the research are still, you know, doing research on these things. But in US, we can see lot many medicines also. These quantum computers can give the medicine to the diseases, just like in some cancers, till now we don't have any medicine. But using this quantum computers without any errors, we can get the medicine for this. I mean, lot many scientists still working on this to get the proper medication for lot many diseases. You can see lot many diseases which we are having, that diseases is not having any medication. Some people may die because of that. But using this quantum computers, we can get the medicines because it give that solution to our daily lifestyles. So quantum computers are that much ease to our lives. Coming to the next slide. Overcoming a quantum hardware challenges to unlock the future. Same thing. Twin pillars. The major struggle which we are facing is that twin pillars. You can see the structure here. Qubit stability and scalability are the foundation for practical quantum computing breakthroughs. The major thing is that qubit stability. In the first slide, which we have seen before, qubit stability and scalability. That both things are the major problems in this quantum computers. So that should be overcome. The second one is that integrated progress. Success demands breakthroughs in hardware design. Trust me, though hardware which is there in the quantum computers, it is very complex. I mean, we can't design in a proper way. So that should be integrated. Control systems and software tooling working together. So definitely, the success of this quantum computers need this integrated progress. This all should be done so that we can get the efficiency. Without this, we are not getting the complete efficiency from the quantum computers. The other thing is that quantum revolution. Solving these challenges will unleash transformative computing power across industries and scientific discovery. If we are getting all the solution to this challenges, then we can see a great life at scientific discovery and industries. In the industries, just like I'm working at Accenture. At Accenture, we can see lot many projects, everything. Without people, this quantum computers can be done all the projects in a very less time. Trust me, 1,000 people are working in some projects. But using this quantum computers without these errors, they gonna work in all the. I mean, they're gonna close all the projects in very less time. Very less time. Because of this, they may lose lot many jobs. I mean, 70% jobs gonna be laid off because of this quantum computers. But 1,000 people's job will be done by one quantum. So that is a big thing about this. So these are the topic for today's session. Can I know some questions regarding this, at least now? Act- Actually, I left last 15 minutes is for questions, Q&A session. But yeah, I'm expecting anything you can ask as I'm the HR. You have multiple questions regarding any of it. You can ask actual questions also. No, limitations for it. You feel free to ask the questions. I see. Sure, ma'am. So, thank you so much, ma'am. Pleasure is mine. Sure, ma'am. Thank you. Thank you all. Thank you, ma'am. Thank you.